Welcome to Roger Klang's math from my book, The Causation and the Universe, a bridge between the 1900s and the 2000s. The P problem and the NP problem in math. What is a P problem and what is a NP problem? Class P, polynomial time. Problems in class P can be solved by an algorithm that runs in a time that is bounded by a polynomial function of the input size. This means the time to solve the problem doesn't grow too quickly as the input gets larger. Example: 2a plus 5b is a polynomial of two terms in two variables a and b. Class NP, non-deterministic polynomial time. Problems in class NP have solutions that can be verified or checked to see if they are correct in polynomial time. However, it's not necessarily known if a solution can be found quickly. Explanation: a problem is called NP, non-deterministic polynomial, if its solution can be guessed and verified in polynomial time. Non-deterministic means that no particular rule is followed to make the guess. If a problem is NP, and all other NP problems are polynomial time reducible to it, the problem is NP complete. This is supposedly a P problem in math. A robot wants to find truth, and it stands before a fork in the road, supervised by an undefined truth-telling equipped or unequipped person. The question the robot must ask the supervising person, if the robot is to reach truth, is: which path leads to your home? Truth-teller would answer, this path, pointing in the direction to truth-teller's home. Liar would answer, that path, pointing to the same path as truth-teller, thus leading to the truth-teller's path. Except, why would a compulsive liar from hell agree to send the truth-seeking robot into the right path? But isn't this rather an ethical puzzle which should be sentenced? Can you ever trust a moderate liar? It doesn't look like you can, because if the lying person at the fork in the road can both lie and tell the truth depending on his mood, there is no way to tell whether any of the two possible fork-guarding persons consistently tells the truth. This should entail that humans and robots cannot trust humans, which leads to the conclusion that you cannot even trust my conclusion, that this leads to my conclusion, that you cannot even trust my conclusion, that this, and so on. So we are stuck in a loop. Maybe hell is a continuous loop in which you live your lies over and over again, like in the movie Groundhog Day. Is it impossible to solve the puzzle with certainty anyway? There may be a solution for the problem, since there is a road to truth. All jokes set aside, even an NP problem must have a solid solution to every fork in the road. There cannot be illogical solutions to any P or NP problem. Let us make this into an NP problem. It must be possible to write an NP problem in code, or the problem isn't possible to solve with logic but would be random. But it is possible to unravel a certain lucky robot's path to truth, even within an NP problem. If you have the answer, just follow the road back and you will end up at the start, since there is only one road to follow in reverse. How do I know that there is only one road to follow in reverse? Because even though solving a Sudoku problem is really hard because it's presumably is an NP problem, I can check if a solution is correct within a very limited amount of time. The only way for the robot to reach truth with certainty above 50% in the binary setup truth-teller-liar p-problem chart above to the left is to ask the question, which path leads to your home? But by asking this question, chances immediately jumps to 100% and becomes certain. However, even with the uncertain liar, chances are 75% prior to entering possible paths for the robot to reach truth, according to the equation 100 times 1.5 divided with 2. If and only if robot is allowed to consider both possible fork guards answers. When clueless because truth teller and uncertain liar point in opposite directions, the robot is going to have to take a guess. But it is needed into the existing 75% probability for the robot to reach truth. Another way to put it is like this. If switch 1 is set to on in A, and the robot asks the question, secluded, to the truth teller A at the fork in the road, which path leads to your home? He can only receive the answer leading to truth. That is 100% probability in switch A. If switch 1 is set to on in B, and the robot asks the question, secluded, to the uncertain liar B, which path leads to your home? He will receive a 50% chance of reaching truth, and a 50% risk of ending up at uncertain liar's home. The robot is allowed to consider the answer from both A and B. According to the equation 100 times 1.5 divided with 2, if he follows the directions given to him while switch is set on B, he will have a 75% probability to reach truth. When combined with truth teller answer while switch is set on A. Of course, the robot has no way of telling which one is the truth teller and which one is the uncertain liar. Not until he sees who is pointing consistently in one direction every time. But the robot won't come down that same fork in the road twice. But if both A and B in the same direction, but if both A and B point in the same direction, there is a 100% probability to reach truth, since one of them always tells the truth. If A and B point in different directions, there is only a 50% probability to reach truth. What I am in effect saying is that with prior knowledge, with clues, you can up your chances. Because if you are a controller located at the robot starting point for both choice of paths, the robot can take, and you can supervise the answers of both truth teller A and uncertain liar B, then you have a 75% probability on average to reach truth teller's home. Note that you still don't know who is the truth teller and who is the liar, since you only get one shot at it. By knowing your prior position and monitoring the future given directions from both A and B, you are following clues in an arrow of time. Thus, an NP problem like this appears to have a probability state solution based on prior knowledge. This may add a dimension for understanding quantum mechanics. Falsify it if you can, but recognize it if you cannot.